657 is, well, right about there. Okay. Then we had 489. Oops. Where's 489? Right about in here. What color is that? It's like that cyan color. Yeah. And then the next one, jumping from the 5th down to the 2nd energy level, was 435. Oops, I went the wrong way. 435 would be right about there. And that's purple. Yeah. What you just calculated, the jumps of hydrogen's excited electrons down to the 2nd energy level, those are visible. Those are in the visible range. We should see, when we look at hydrogen with something that separates the colors of light, we should be able to see those specific bands of light. Now, I didn't have you calculate the 6th to the 2nd energy level. That would be the one that's in the very deep purple range that was hard to see. So here's what I'm going to do. I want to show you that for real. I have some diffraction grading glasses. These are great. When you take it, you've used these before, I think, in Chem 1. I'll do it up here. I'll turn the smart board off for this. But take these. Please don't put your hands on the lenses. Whoops. Or the lens on the floor. I do it all the time. Yeah, so look at the white light. Maybe turn around and look outside. I am going to try to close those blinds.
Really? You only have 2?
So I'm going to try to make it as dark as I can in here. Of course, we have a nice, bright, sunny day for this. All the gloomy days that we had that would have been great for this activity, I squandered. So now we have a bright day, unfortunately. Nah, it's really not unfortunate. It'll be fine. Now here's what is cool. When I turn the light off, take your camera, your phone out, and turn the flashlight on and check out the flashlight. Real bright light with that. It's nice.
Flashlight on your phone?
Yeah, like this.
Oh, the smart board.
Look at that. Oh man, that's so nice.
What is going on?
Whoa!
So I'm going to put this to bed for a moment.
Yeah, Mr. Moore, look at mine.
I don't have my glasses on yet.
Mine looks whack.
Oh, yeah.
That's whack. That's cool.
This is really
Whoa, check out my flash though.
Ow, my eyes hurt.
Oh my goodness.
really rotating. Okay, my light.
Yeah, if I went to a party, I went to wear these glasses.
Yeah.
Yo, can I cash snack or was something?
I will. I'll do that. Can I borrow one? Is it okay with you? Do you want to use the yellow?
We had hands on. What? Or what are you saying? Yeah.
Oh, yeah. Oh, I'll need one more or two.
Well, you want one more?
Not from you, though, right?
Oh, I have an extra one.
Oh, thank you, Lauren. Okay. So now this is what Niels Bohr saw when he was analyzing hydrogen. Like I said yesterday, he wasn't able to look at a hydrogen atom. They're too small. So he was looking at hydrogen indirectly. He was looking at hydrogen when it's heated up. Oh, yeah. Oh, my goodness. No, this is no good. I guess it's okay. Now, you see a whole bunch of secondary bands. Look not at the secondary lighter bands. There's some that are very bright. There's the red one that's real bright. Can you see the real bright red one in that left and right from the light? There's our 600, I forgot it now, 657? That was our one that's 657 nanometers. Then there's that cyan. That was the 400 whatever. Oh, yeah, there we go. And, well, Yeah, I was going to say, it should. Sorry for Johnny. Oh, yeah. Yeah, it is. Not very good.
Yeah.
Yeah.
On the different things,
So,
red one's brighter than the rest. Yeah, that's yeah.
these are El Cheapo diffraction gratings, obviously. Niels Bohr would have used one that doesn't have all the secondary bands. He would have seen just those 4 bands of visible light. But he was able to determine, using his equation, what the energy of those electron jumps were. The jumps to the first energy level are too high in energy. They're low wavelengths, because remember, wavelength and energy are inversely related. So a lot of the jumps we can't see, but the ones that we can see show up on here. Just for contrast, I want to show you some other things that would be heated. Like this one is, I don't know if I have a helium. I don't. Oxygen is the next one that I'll show you. So you can see every element has its own spectrum of light that it gives off. Oh man, the oxygen one is pretty weak. I don't know if that one's about to burn out or what. Can't even see a spectrum very well out of that one. I may have another oxygen. The neon one is real cool. Here's another oxygen. Let me try this one. No, that one's dead too. Skipping the oxygen. This one is Mercury. The color of the Mercury is really nice. Now, Mercury has an atomic number of 80. There's 80 electrons that can jump around. Usually it's only the outer electrons, though. Now, remember, we talked about how the farther you get from the nucleus, the closer the energy levels are to each other. With Mercury in the 5th row of the periodic table, 6th maybe, it's in the 6th, it's got electron energy levels that are really close to each other because those are so far out from the nucleus and so many are filled. But it still does have some that jump in the visible region. Look at that baby blue color. Mercury is so nice. And so when we separate those with the diffraction grating, yeah, this one separates much nicer than the hydrogen does.
I see green, orange, and purple.
But the blue, oh my gosh, that's such a nice.
Yeah, there we are. That looks nice. Yeah. Yeah, that is a nice purple. All right. Last one I'll show you is neon. Really, it's saving the best one for the last. Neon is very nice. Yes, this is why they use it in science. Yep. Whoa. Isn't that good? And when you look at it with the diffraction grating, you can see why it has this color. It's got all these electron jumps that are down in the red region.
I see like more multiples. You know what I mean?
Yeah, they're so close together, you just get this blur. I guess you can see them way out. That second set of them, they're more spread out. Oh yeah, it's so good. That's a nice deep green color too. You see the green band?
Yeah, the green, yellow. Oh,
yeah.
Bunch of atoms. Why?
Okay. Yeah, those are cool. But anyway, that's what Niels Bohr used to kind of jump into the fact that energy is quantized. Those electron jumps don't have any old value. You don't get a continuous spectrum. You only get certain bands of light out of them. Matt, would you mind collecting those back for me? I had this, I guess. Yeah, here's this. Thanks.
Can you guys send him to the front?
You gotta turn the lights on. I'm sorry about this. Oh, man, that's wrong.
For the light?
Yes. You don't think so? I had rearranged the order of slides before. Here's our good friend, French guy, Louis de Broglie. Okay, now here is the scientist that we're going to land on for really the rest of the chapter. We talked about Niels Bohr, and Niels Bohr was in no way a failure. He only could come up with a model that represented that of hydrogen. That was, though, when things were just getting rolling with the whole notion of quantized energy. In the 1920s, I can't remember what the actual year was, but Erwin Schrödinger, an Austrian guy, was able to come up with this thing that we call the wave mechanical model. And if I could just go back for a second, this may have been 1925 that Schrödinger did this work. In 1923, it was Louis de Broglie that described particles as if they're waves. Every moving particle has a corresponding wavelength. So that kind of inspired Schrödinger to think of electrons and their descriptions as wave-like. He didn't describe them at all as particles. He strictly described them as waves. So, oh, it was 1920. I forgot I had written the date on there. So he's kind of standing on what the work that de Broglie did. This math that Schrödinger used was very complex, past three-dimensional calculus. This would be like a third-year college course topic. You've got to kind of have the math catch up with most people. I know some Troy High grads will walk into college having already taken Calc 3, the multivariable, but a lot of people will not. So this is, like I say, a third year. In chemistry, in a chemistry program, you would study this in physical chemistry. We call it P-Chem. You would have strictly a quantum mechanics course in a physics program or an engineering program. If you like physical sciences, you'll really enjoy taking this. If you want to be a doctor, you would not like this. Schrödinger was not the kind of scientist that was sitting in a lab with test tubes and lab equipment. He was paper and pencil kind of scientist. He's a theoretical scientist. In his description, he has this spectroscopy evidence, like what Bohr came up with, but for all elements. And he developed a model that really was based on probability. He came up with, okay, electrons have a high probability of being found in this region and not in this other region.
What are those symbols?
Yeah, what are the symbols? This thing right here is a Greek letter. It's capital Psi, like the trident kind of a picture. Yeah, that's a psi. And so down here, the E is the energy of the wave function psi. And this thing over here, the H with a hat on it, that's called a Hamiltonian operator. I don't know if Schrödinger actually had to develop the math that he used for this, but it was quite complex. It's called an operator. And the operator would... it would give a set of instructions to something called an eigenfunction, and you'd get eigenvalues out of it. I mean, yeah, it was strange. Back in the day, I was a math minor, you know, and I had gone through all those math classes that a lot of you will go through. And this made all perfect sense. Well, in the last 20 or so years, I have forgotten all the calculus that I learned, and so this I would have to really, if I needed to teach this, like in a quantum course, I would have to go back and spend an awful lot of time reviewing. It's just gone from my brain because I haven't used it at all. At the time, when I was up on the math, it made perfect sense, and it was really fun. I know how dumb I'm going to sound, but it was fun to do the problems on this because we would have to make a graph, and the graph would, using the Schrödinger wave function equation, we would solve the equation and make a graph.